I'm Silva. I'm here in Nigeria, and I'm a lecturer and researcher with WSN Medical University here in Nigeria. So I'm actually presenting on a topic titled Presenting Data and Measuring Relationship Between Variables. So basically, the content of my presentation is a brief introduction of statistics, presentation of data, and statistical relationship and most used measures. The course objective, this material is actually designed so that at the end of this presentation, participants will be equipped with basic knowledge of statistics, basic knowledge of tables, basic knowledge of graphs, and basic knowledge of most used measures of relationship between variables. So I think the first question we should ask ourselves or remind ourselves is what exactly is statistics? In the simplest term, statistics is the study of data. That's how simple it is, that the whole business of a statistician is studying data. Then how do we study data? But before we look how we study data, what exactly is a data? Data can be defined as any numerical or categorical measures from statistical experiment or observations. That is one way to define data, as a numerical or categorical measure from statistical experiments or observations. Since we know what statistics is and what data is, how do statisticians carry out this study? Number one, we study data by collecting it, we analyze it, we interpret the result, and present findings. So basically, we can define statistics as the collection, the analysis, interpretation, and presentation of data. How do we present this data to both statistician and non-statistician? Data are actually presented in three ways, basically. Either they are presented in arrays, tables, or graphs. We'll take just an introductory background of graphs. What exactly is a graph? Since it's one of the ways we present data, what exactly is a graph? By my definition, I say a graph is a representation of data diagrammatically. A graph is a representation of a data diagrammatically. There are different types of graph. We'll just look at very few because of time. So I say there are 5 basic types of graphs that are used mostly in statistics. The first is the area graph. The second is the column graph. We have the bar graph. We have the line graph. And we have the pie graph. Each of these graphs are used to fit basic needs, depending on the nature of data and what exactly you want to report. But these are the most used graphs in statistics. Now, graph decisions and guidelines. When you are deciding on which of the graphs to use for your presentation, the decision tree will always be of great help. The key question to consider are whether the data is time sequence based or how many data series you want to show. Selecting the appropriate graph helps in making the presentation clearer. Before we look at the guidelines, we made mention of data series. I think we should look at the definition. And I've carefully defined it as a set of related data is referred to as a data series. For example, the sales of a car each year for the past 10 years would be one data series. Let us also look at key components of a graph. The first I have highlighted is the color. I decided to make mention of color because it's of great importance while reporting data with graphs. I have stated clearly that we have to make sure that you set the background color and the color of each data series so that there is enough contrast to be seen clearly. This color should also be consistent with the overall color scheme of your slides or your presentation so that the graph does not look like a fallout. Also, I mentioned the depth. By depth of the graph, I've referred to whether it is in 2D or 3D. Whether your graph is in 2D or 3D is a key component you always have to put in mind. And the axis. All of the above graph type except the pie graph, all the ones mentioned apart from the pie graph, has two axes. One is for data value and the other is for time scale on how the data is separated. It is important to set the scale of the axis to the appropriate data being shown. Also make sure that the axis labels, they indicate the value along each axis as big enough so that it will be very clear. So when you are setting up your presentation using graph, you have to consider the color of your graph, you have to consider either 2D or 3D, and you have to consider the axis. Another thing to consider is the data label. When you need to be more clearly on your presentation, the graph must be labeled. This is a label is a text box that contains the actual data. I mean the value. You see some graph where you see like a bar standing and the exact value of that bar is presented. For clarity, that value is called the data label. So it is advisable if you want clarity, most times you are presenting data to non-statisticians, that the graph be labeled. And I also made mention of the title. The title of the graph should focus on interpretation of the data and not the data itself. For instance, if you collected data for diabetes and you are presenting the graph, you should state the graph you are presenting, not the data itself. Graph of female diabetic patients in Nigeria will be a better title than stating the raw data. Remember that we are always using graph to help make a point. So the title is always a very important factor in clarity. I've carefully flowcharted a guideline in picking the best or appropriate graph while presenting the data. It starts with, is the data time sequenced? If the data is time sequenced, if it is yes, what is the number of sequence? Is the next question you ask yourself. If the number is between 4 to 6, a column or line graph is most appropriate. If the number of sequence is between 1 and 3, the next question you have to consider, do you need to show relationship? If the answer is yes, the area graph is most appropriate. But if no, then you have to consider a line graph. On the other hand, if the data is not time sequenced, the next question you have to ask yourself, what is the number of series? What is the number of series? If you just have one series, the next question you need to consider, do you need to show or do you want to show relationship? If yes, a pie chart is most appropriate. If no, a bar or column graph is the most appropriate. But if the data is a series and you have about 2 to 3 series, the most appropriate graph to consider is the bar or the column graph. And if the data series is between 4 and 6, the best way to report such a graph, such a data, is using a table. This will lead us into the second procedure or second way of presenting data. Remember, we made mention of the array method, the graphical method, and the next is the tabular method. So tabular presentation of data is the method of systematically and logically arranging the data in the form of rows and columns with respect to the characteristics of the data in mind. There are different standards and style in representing data in table based on the need. But basically, the structure of a table is a set of columns and rows that contains the data and usually contains either a row or a column or both of heading that organize the data. When deciding on the size of your table, it is good idea for you to keep in mind what statistician title or called the 6x6 guideline. By that we mean that it's most appropriate for you to report a data at most using 6 rows and 6 columns. We are not saying it can't go beyond that based on the need, but most appropriately, the 6x6 guideline should set out a table with 6 rows and 6 columns. We have to consider in selecting the table size of the data, make sure that your font size of your text in each cell of the table is big enough to be read clearly when displayed. When you use a table to present a data, you will need to provide interpretation of the data. One way to make certain cells stand out in the table is to highlight it and color it, or sometimes bolding it. We use those color variants just to show emphasis on a particular column or a particular row. I will always want us to consider one special kind of or a style of table that is famously known as the APA format, that stands for American Psychological Association Table Style, the 6th edition. The structure of that table, which is globally accepted, is one, numbering. The tables must be numbered. If you present a table, depending on the number of tables you are presenting, you see table 1, you see table 2, you see table 3. APA standard of table is that every table must be numbered. Secondly, there must be a title. The tables must contain title placed one double space below the table number. After you have titled the table, after you have numbered the table, the next thing that will follow is the title of the table. Every table in APA standard or APA style must have a title. After that, the table must have a heading. Each column must properly be headed, including the rows if you have rows, stating clearly what they stand for. Table must include a variety of headings depending on the arrangement and the nature of data. And we have thirdly the body. The table must include a well-labeled rows and columns like we mentioned. And lastly, that is not here, the footnote. Every table must have a footnote. Let's take, for example, a table I'm presenting that I designed just for demonstration. You will see table 1. This is exactly the number of the table. Directly under it is the title of this table, the number of people living with diabetes in Nigeria. And we have considered gender, body mass index, and family history, underweight, overweight, normal weight, yes or no, as different headings. Under it, you will see the note. The table was created just for the purpose of demonstration. This is exactly a typical APA table style, 6th edition. If you look at it, you will see that we have basically 6 rows, 5 rows and 6 columns. With the guideline I said in mind, the 6x6 guideline, we have a clear table here reporting everything that is needed, and it's just a 5x6 table. So every table, we have different standards, but this is the APA standard and it's globally accepted. You must have that in mind. There are no borderlines within borderlines, and it must have the title, it must be headed, it must have a footnote, and it must be numbered. The next stage of our presentation will be the statistical relationship of variables. I have deliberately not mentioned the method of arrays as simple as ABC, which statisticians know whenever we report data in an orderly manner, either in ascending or descending order, it is said to be in arrays. Those are basically the three methods statisticians report data. It's either in arrays, graphical method, or by tables. So that done, my next slides will be looking at statistical relationship. What is statistical relationship? I always start every key topic with a definition or just give it a background for we to know exactly what we are looking at. A statistical relationship is said to exist between variables if a change in one results in a systematic change in the other. The change is said to be systematic because it's not a constant, it's not even, it's irregular. Means for every 1 unit increase in the first variable may not necessarily mean a 2 or 3 unit increase in the next. That increase may be irregular. That's why we say systematic, depending on the nature of the data. The unit of change may not be constant, is what we are saying. We have different types of relationship, and that will be considered in our next slide. I have presented this in a simple chart, starting with what I have called relationship analysis. Coming down, we'll see, after analyzing the relationship, there's a possibility that the variables are unrelated. You cannot use one to explain the other. A change in one means nothing to the other. There is no relationship at all between these variables. Whenever that happens, after analysis, you can say the variables are unrelated. Secondly, there is a possibility that they are related. If a change in one accounts for the change in the other, we'll say these variables are related. And we have different kinds of relationships. Just like in real life, the relationship men have with different people, so also data are related differently. Once they are related, the next question we ask ourselves, what is the relationship like? The relationship can be basically in two ways. It's either it's linear or non-linear. If it is linear, there are two options we need to also consider. Is it positive or negative? If it is non-linear, is this U-shaped relationship, curvilinear relationship, or inverted U-shaped relationship? I have considered each of these relationships in my next slide. The first I've highlighted here is unrelated variables. Like I said, variables are said to be unrelated if there is no systematic relationship between them. That is to say, change in one variable is not related at all to change in the other. The second highlighted here is a linear relationship. Linear relationship exists between variables if the variables can be explained by a straight line. If this relationship can be explained using a straight line, the direction of this line tells if the change is positive or negative. I have shown clearly the two kinds of relationship. The first is positive relationship. Where an increase in one variable causes an increase in the other, those variables are said to be related positively. And if you plot it, you have a graph like this one on my left. When an increase in variable x accounts for an increase in variable y, that kind of linear relationship is said to be a positive relationship. But when an increase in variable x results in a decrease in variable y, or a decrease in variable x result to an increase in variable y, that kind of linear relationship is said to be negative. So whenever we have a relationship where once this variable goes up, it results in the other one going up, we are looking at a positive relationship, and otherwise it's said to be a negative relationship. I've also highlighted the curvilinear relationship. Depending on the nature of data you have collected, curvilinear relationship between variables can generally be presented or explained by curves, not a straight line. This means that the relationship takes at least one turn or curve to represent the data. These curves include but not limited to, it could be quadratic, it could be cubic, it could be quartic, or quintic, depending on the kind of data you have collected. If the relationship does not show or cannot be explained by a straight line but a curve, such a relationship is called curvilinear relationship. Another one we'll look at is what I've called the U-shaped curvilinear relationship. A U-shaped curvilinear relationship means that two variables are related negatively up until a certain point and then start relating positively. Means at first, an increase in one result to an increase in other. It will be in that order until a certain point when an increase in one means a decrease in the other. Such a relationship is said to be U-shaped curvilinear relationship. And we have another titled the inverted U-shaped curvilinear relationship. An inverted U-shaped curvilinear relationship means that the two variables are related positively up until a certain point and then are related negatively. At first, an increase in one means an increase in the other. To a certain point, when it will turn to an increase in one, result to a decrease in the other. Such a relationship is said to be an inverted U-shaped curvilinear relationship. Statistically speaking, there are many ways we measure relationship in statistics. I've highlighted just one I have recalled, but first thing first, I would like us to look at the term measure in statistics. The term measure of relationship or measure of association is sometimes used to refer to any statistic that expresses the degree of relationship or strength of relationship between variables. I'll say it again. The term measure of relationship or measure of association is sometimes used to refer to any statistic that expresses the degree of relationship or strength of relationship between variables. There are different procedures or statistical methodology to measure the strength or degree of relationship between variables. And one I've highlighted here is the correlation coefficient. It's a numerical summary of value used to measure the type and strength of relationship between variables. The correlation coefficient is a numerical summary of value used to measure the type or strength of relationship between variables. It is of the form rho subscript xy, where xy is showing the two variables under consideration. Is equal to plus or minus and a k, such that -1 is less than or equal to the correlation coefficient, which is in turn less than or equal to 1. Where the sign plus or minus is used to indicate the direction of this relationship. Direction, by that we mean if it is either positive or negative. And the k is a numerical value used to show the strength of the relationship. We'll just take a simple example that the coefficient of correlation ROXY is equal to 0.87. Shows a strong positive, the sign here is plus sign, and the strength of it is 0.87. So this shows a strong positive relationship between variable X and variable Y. I have also highlighted the most used procedures in calculating this correlation coefficient. Researchers use different statistical procedures to calculate correlation coefficients depending on how the variables are measured. I have highlighted a few. The first is the Pearson product moment correlation coefficient. It is used most appropriately when both variables are continuous. By continuous, we mean the variables are either interval or ratio. Secondly is the rank order. This is used when both variables are ordinal. I have also highlighted the point biserial methodology or procedure, which is used when one is continuous, one of the variables is continuous, and the other one is nominal. And we have other methods like the biserial listed, defy, contingency, tetrachoric, and eta. All these are different procedures for calculating the coefficient correlation to show relationship between variables. But because of time, I have highlighted in my presentation the Pearson product moment methodology. The most commonly used type of correlation is the Pearson product moment correlation coefficient. It measures the relationship between two continuous variables. It is denoted by rho and defined here as ROXY, that is the Pearson correlation coefficient between two variables X and Y, is equal to N, which shows the number of data, summation XY, the interaction between the two variables, minus the summation of X multiplying the summation of Y. This divided by the square root of N summation X raised to the power of 2, that is X squared, minus summation of X all squared, multiplying N summation of Y squared minus summation of Y all squared. I have highlighted a scenario to illustrate or demonstrate the procedure of Pearson product moment correlation coefficient. Taking for example, a sales company was interested to know if there is a significant relationship between advertising and sales. This information will help management in deciding the advertising budget for this year 2021. So they collected the budget for advertising and sales record for corresponding years and sent it to a statistician to analyze and report. The first thing is to receive the data, which is the collection stage, and we've collected the data. And from the data, I've titled this table, Table 1. I've numbered it, Table 1, and titled it Advertising Budget and Sales Record for Silver Distribution Limited Company. So for the different years collected, we have from 2014 to 2020. For the year 2014, the company budgeted 25 million for advertising. And in that year, they recorded a sales of 55 million. In 2015, they budgeted 35 million for advertising, and sales went up to 76 million. As listed for 2016, for 2017, for 2018, 2019, and 2020. For 2020, which is last year, they budgeted 60 million and recorded sales of 122 million. I have a footnote to this data that the data is fictitious. It is for illustration purpose. I have used the data received to calculate the Pearson correlation coefficient. I have labeled the advertising budget X, and I have labeled their sales record Y. The interaction between those two variables, that is X, and squaring the variable X gives a new column X squared. And squaring the variable Y gives a new column Y squared. Summation of Y is summing along the summation of X is summing along the column X. Summation of Y is summing along the column Y. Summation XY is summing along the column XY. Summation X squared is summing along the column X squared. And summation Y squared is summing along the column Y squared. N obviously is equal to 7. Inserting that into the correlation coefficient, the Pearson correlation coefficient formula earlier highlighted, you see we have 7, which is N, multiplying 41,655 minus this product, divided by the square root of the denominator. Simple arithmetics will produce 0.95 as the Pearson product correlation. The next is interpretation of this result.
Okay.
Pearson product moment correlation coefficient shows that there exists a high significant positive relationship between advertising and sales. But this does not necessarily mean that advertising is the cause for the sales. That is why there is a big difference between correlation and causation. I would have loved we other methods, but for and for this presentation, I treated the Pearson product moment correlation, and I've referenced what the making of these materials, which I highlighted here. And this is all for my presentation. I want to thank the organizers of this platform for giving me knowledge with others around the world. I don't take things like this for granted, and I'm most grateful, and I always make myself available whenever I'm called upon to deliver such lectures. Thank you, and God bless you.